So here we are, and we're studying capacitors today. And as I roll through, so in a nutshell, capacitors can be used as an energy storage device, but they're more often used as a signal processing device. They come in all sorts of shapes and sizes. We tend to look at parallel plate capacitors that are filled with a simple dielectric, and we'll get to what that is. So we say a capacitor's capacitance is the magnitude of the charge stored on one of the plates per the volt of potential difference applied across it. So let me get my pen. So I'm imagining some kind of battery, and I'm imagining a parallel plate capacitor. Now, in truth, I just want to set ourselves up. It's tempting just to draw that like that, and that's okay in principle, but in practice, there's always a bit of resistance around, so you should really draw it like that. If I have 6 volts here, when this thing is fully charged, I have 6 volts across here. Here I call it EMF. Here I call it potential difference. But it's 6 volts in both cases. This would be 0 volts potential difference once I'm fully charged. So, question is, what's the capacity of that capacitance? And we say, well, take the amount of charge you have on it and divide it by the potential difference across it. So we say the capacitance equals the charge divided by the potential difference. If I apply more potential difference, so let's visualize this. I start off with an empty capacitor, there's no charge on it. I have my battery. The battery gives the charged particles energy. And what happens is there's no charged particles on here. You give your first charged particle energy. Oh, that was easy. So the positive goes to one parking lot and the negative goes to the other parking lot. To get the second charge on there is harder because it's got to come close to the first charge. To get the third charge on here is even harder. To get the fourth charge on here is even harder. To get the fifth is even harder. To get the sixth is even harder. And I don't have enough energy in this battery to get the seventh charge on there. So I'm fully charged. It's like the parking lot is full. But if I somehow increased the EMF of the battery, oh, now I got stronger charges. So, oh, now I can get a seventh. I can get an eighth, I can even get a ninth, and now I'm fully charged. And if I went to a 10-volt battery, I'd have another one. In all those cases, it's the same capacitor. And so in the first case, I'm going to cheat here, I'm just going to use simple numbers. I'm going to say the capacitance equaled 6 coulombs over 6 volts, which equals 1 farad. In the second case, I had the capacitance equals 9 coulombs over 9 volts, which equaled 1 farad. And in this last case, I had equaled 10 coulombs over 10 volts, which equals 1 farad. So I've not increased my capacitance, I just increased the EMF that the capacitance was exposed to. But I can increase the capacitance, and that is by doing some physical tricks. Have you got a question or a comment at the back? Yeah. Capacitors are mainly used for signal processing, yeah. If you were to count the number of capacitors in the world, most of them are doing signal processing tasks.
What does that mean, processing?
Basically, they might be used as an AC filter or a DC filter. They might be used in a tuning circuit. They're used as some way of controlling the voltages inside an electronic circuit, as opposed to being used as a battery inside a system. So capacitance. Now I can increase the amount of charge that I can store on a given for a given EMF by changing the design of the capacitor, and we're going to talk a little bit about that. So capacitance is like a figure of merit. It is measured in farad, and this is measured in coulomb, and this is in volts. Comment or question?
Sir, does the path difference matter?
Does the what matter?
Path difference.
path difference.
You said here, PD.
No, potential difference.
Oh,
Sorry, potential difference. The potential difference does matter. That's what drives the charge. Well, the EMF drives the charge onto the capacitor. As the amount of charge on the capacitor increases, so the potential difference increases. Cool. Yes.
So what if you had the 9-volt power supply, but you had a 6-volt capacitor?
Oh no. Capacitors are measured in farads.
Or sorry. You had a smaller capacitor that, say, could only have a 6-volt potential difference.
No, you can put whatever potential difference you like. So the EMF is what I apply. That's my power supply. That's your choice.
Yeah.
And when it's fully charged, the potential difference will always match that EMF. Okay.
So what happens, or what's the difference, I guess, if you have the same size capacitor but a higher voltage, then
You get more charge on there.
you just get more charge?
Yeah, because you can put more energy on it. You can put more charges on it. I'm sorry, not energy. You can get more charges on it.
I guess the diagram is confusing me then, because it seems like you have to make the capacitor larger to fit more charges on there.
No, I didn't change my plates. I just changed my number of positive signs. My plates are still the same size.
Okay.
Yeah. So, and that's what I was trying to get to actually is, the capacitance is the capacitance. You can mess with that physical situation. You can change the EMF and you get more or less, more charge on if you increase it, yeah? If you want to get more charge for the same EMF, you've got to physically mess with it. And that's where we're going to go. Yes?
Let's say you had, like, they have voltage ratings. Let's say you had a higher voltage and the voltage rating of the capacitor was lower than the voltage rating. Would it destroy the capacitor?
So what happens is, when you're fully charged, your potential difference is the same as the EMF.
Gotcha.
So let's say I have 1,000 volts across here. They're not very far apart.
Yeah.
So at some point, I'm going to get a thing called dielectric breakdown,
Yeah.
where these positives are going to say, man, I just want to be with those negatives, and man, I don't care about the gap.
Yeah.
And so you get a spark if it's just a gap in the air. If you filled it with paper as a dielectric, then you'll burn a hole
So basically, it's
through the paper. And what tends to happen is, although you might think you burn a hole and then, so fine, just turn down the voltage. I think typically what happens is you make a typical conducting path, and then it's short,
Yeah.
the capacitor's short, yeah. So that's why you will see them having voltage ratings saying, don't go above this voltage, because it's not rated for above this voltage. Cool. Just a word. So we're going to see this again in a thing called Ohm's law, which we'll get to later. So I think there's a couple of questions that have raised an issue, which is, what do you control? And I remember when I was a student, it wasn't obvious to me what I controlled. It was just an equation, and all bits of an equation, you can mess with any number, and as a teacher, you can mess with any number. But in practical terms, you pick a capacitor out of a box, and you decide what voltage to put across it, and you get eventually what charge it can stand. So you're choosing the C and you're choosing the delta V in your experiment, and you get whatever charge you get. You can't so easily say, I'm going to have 10 coulombs of charge as one of my variables. You can't just dial up 10 coulombs of charge. It's what you get. And sometimes I think it's important to realize that, especially in the lab. There's some things you have control over and some things you don't have control over. And I remember I just didn't get that until I was quite far on in my studies, and it was like, I can't control that. So how much charge can a 9 picofarad capacitor hold when a 4 millivolt potential difference is applied across it? A bit of language here. I'm trying to tighten up on my language. So I would probably rewrite this question. This is a 4 millivolts. So, I got to be okay. So this is, let's explain what I mean. So this is my resistor, and that's my capacitor, and this is my battery. So I have 4 millivolts EMF. That's what batteries provide, electromotive force. And I can tell you now, oh, I'm sorry, no. I have VEMF. Let's say I don't know what it is, it's big. And that means that I'll get V potential difference from the top of this to the bottom of that. Because what you create in the battery, you spend in your circuit. But in this case, I chose to draw 2 components. Now, they don't both get V volts because they're in series. So one of them gets part of V and the other one gets the rest of V. So I need a way to talk about the voltages on this side as distinct from the voltages on that side. So when it's to do with a battery, I call it an EMF, and when it's to do with a component, I call it a potential difference. And all I'm saying here is that the potential difference across that is 4 millivolts. So this would be V minus 4 millivolts, because they've got to add up to V. Does that make sense? So sometimes I'll talk about potential difference, and sometimes the potential difference equals the EMF. But often it does not. Often the potential difference across this component is just a part of the numerical value of the EMF. So I'm just trying to lay that foundation. But I know that that's 4 millivolts. I know that capacitance, the capacitance is equal to 7 picofarads. So I'm going to say, okay, how much charge? Well, capacitance by definition is equal to the charge per volt. So therefore charge is equal to the capacitance times my voltage. So charge is equal to the capacitance, which is 7 times 10 to the minus 12, thank you, times voltage is 4 times 10 to the, yeah, okay. So that's going to be equal to 28 times 10 to the minus 15. What's the units? Coulombs. Which raises an issue, of course. So let me get this sorted out. Capacitance is measured in farads and charge in coulombs. Can you see a huge problem? So what some people do is they get used to doing curly C's at times, and you just got to be careful about it. That's why an intelligent, casual student will mess up, because they don't know what the letters stand for. You know, if you're smart and you can usually figure things out on the day, you know, it's almost like we're just trying to catch you out. We're going to use the same letter for 5 things, and you're going to make a mistake over it because you're not going to understand what it means. So just watch out for that. Be careful for that. Make sure when you see an equation or when you see a parameter, you know what it's talking about. Okay. Which trace best represents the relationship between a charge on a capacitor and the potential difference? So here we have, I'm going to draw it again. I have my Q. And so that's charge in coulombs. So it's C. Casual observer gets caught on that. And this is my potential difference, which is going to be in volts. So where's my linking relationship? Oh yeah, charge is equal to C times delta V. We'll call this delta V for consistency. And there's one variable. I usually try to write it in a different color to make it stand out. What I do, having got my equation, is I come along here and I go to a different color. And I say, well, there's one variable. And there's the other variable, and then I see what kind of relationship I have. And what kind of relationship is this? It's linear, isn't it? Linear. And so I can say it's going to look like that. But that's also linear. So which one is it? So what he says is, as V increases, Q increases. So it's going to be that guy, yeah. But that can catch people sometimes. Later on, and there's not much later on actually. Later on, I'm not going to give you that. I'm just going to give you that. And I'm going to say, plot a graph using at least 3 points. And you've got to decide. I'm going to give you a grid. Usually 4 by 4, because that tends to work out quite nicely. I'm going to say, give me some numbers. Figure it out. And people are going to turn around to me and say, what numbers? And I'm going to say, that's the point. It's like, you got to decide. And they go, but that's crazy. There can be a whole bunch of answers. And I go, I'm a smart guy. I can figure it out. As long as you write down the numbers, leave the rest up to me. And it's a very uncomfortable feeling not to be given numbers. But when you're in a job, you're not given numbers. You're just given a situation. You've got to figure stuff out. So what I say to people is, what you do is, you first of all do a column, which is Q, and you do a column, which is delta V. So we're back. Let's give it just a couple more seconds. And let's see. Boom. Most people saying a little bit of the others as well. So let's go from here. So we can say, well, our base equation, of course, is that the capacitance is equal to K A epsilon naught over D. And what do I know? I know that my A is equal to pi r squared. Okay. So that equals pi times r, and radius 4 centimeters. So that would be 4 times 10 to the minus 2 squared. So there's my area. And let's have a look. My K was equal to 1, and my D is what I want to find. And what's my capacitance? My capacitance is equal to 3 times 10 to the minus 6 farads. So let's rearrange. D is equal to K A epsilon naught over C. So D is equal to 1 times pi times 4 times 10 to the minus 2 squared times 8.8 times 10 to the minus 12 all over 3 times 10 to the minus 6. And at that point, I'm just doing calculator work, and it's a shame. So I just go nice and steadily. So I simply go, and I'm just very pedantic about it. I just go very step by step. I go 1 times pi equals times, and I'm going to do this the slow way, 4 second EE to the minus 2, enter, times 4 second EE to the minus 2, enter, times 8.8 second EE to the minus 12, enter, divided by 3 second EE to the minus 6, enter. Because I hate losing points for a slip like that. So then I'm going to turn around, and that should be, I'm getting, I've got to count, yeah, it's 1.5 times 10 to the minus 8 meters. Yep, so there's my answer. So I just find it a shame, especially so if you put down all the working and then you make a calculator slip, then, you know, depending on, I'm really picky when you're dividing by two things. So if I have 27 over 3 times 4, I can't tell you how many people will go 27 divided by 3 times 4 and get the wrong answer. You can do 27 divided by bracket 3 times 4. That will work. Or if you do it my way, you go 27 divided by 3, enter, divided by 4, enter. And that will get you the answer. So it's a shame when you make a mistake on that just from a calculator point of view. Okay? Cool. Okay, so the next bit I want to talk about the combinations of capacitors. You might want a specific value. And so, oh, I'm sorry. Let's go back 1 second. I remembered what I wanted to tell you about. Look at that gap. It's really small. It's a bit of a theoretical answer, okay? But the gap in most capacitors, they're rolled. They're like a Swiss roll. They're rolled, and the gap between the plates is really small. If you were to construct that and then try to either fill it with air or fill it with a piece of paper, it's a horrendous job. From an engineering point of view, that's awful. But if you just take 2 long tapes, take a tape of aluminum, take a roll of paper, take another tape of aluminum, and just roll it up, then you need another roll of paper, but you roll it up and you find that the dielectric acts as the spacer. So it's doing 2 jobs. It's spacing, it's creating the gap, and it's filling the gap at the same time. So it's just a nice way. Look at those videos and how you make them. It's very interesting. So now recognize the fact that we might want a specific capacitance for various reasons, and you're not going to go to the store and find there's an infinite number of capacitors. They mass produce these things as cheaply as possible, so they'll tend to make stock values. And yeah, you can go through a whole bunch of bins and look for the nominal value that's closest to what you want. The other thing that can happen is you can deliberately combine capacitors to either make the capacitance larger or smaller. So you might connect capacitors together to adjust the net capacitance. The other thing that can happen is you have capacitors connected together in a certain configuration because of other issues. Just the circuitry requires it, and therefore you've got to figure out what the total capacitance is, the net capacitance is. There's 2 very standard ways of connecting components, parallel and series. And I'm drawing them in very specific ways here. But, be careful, because if let me draw this. God, where's my pen gone? That. If I do that, those capacitors are in series. It's not because they're level on a diagram. Those capacitors are in series. So those capacitors are in parallel. So you've got to get used to kind of like interpreting these diagrams. Question or comment? Pardon?
How are the series capacitors being discharged?
You just connect them together. You go like that. And they get discharged. Yeah, you can do it separately. You can do it all together.
I mean, the 2 electrodes are separate.
So you have a whole bunch of positives here, and you have a whole bunch of negatives there, and these guys decide, I'm going to combine with these guys. And that breaks the electric field down. Then these negatives say, oh, I like those positives. So they combine. And then in this gap here, these positives combine with these negatives. There's a piece of conductor between them. Yeah. So anyway, we've got to be careful about having the capacitors interpreting the diagrams. Think about your expression for capacitance. Capacitance equals K A epsilon naught over D. A, as A gets bigger, epsilon, the capacitance gets bigger. Agreed? Notice. So think of conductors, wires, as being like flexible pieces of elastic. They connect things together. Their length doesn't matter. So I could basically connect those guys together, and that really means that these plates are joined together. So those plates are kind of joined together. Electronically, they are joined together, and those plates are joined together. So I could rebuild this capacitor by making one plate that's the same area. I just increased my area. So can you see how by doing that, I'm basically increasing the area when I add capacitors in parallel. I'm increasing the area, which makes my capacitance bigger. So it makes sense that C parallel is equal to the first capacitor plus the second capacitor plus the third capacitor plus the fourth capacitor. Yep. And here we have them in series. And again, I can kind of like, well, that can just go away. And that can just go away. So I end up with, and connect these two guys together, and they just form one plate. Connect these two guys together, form one plate. Connect those guys together, form one plate. I have positives here. I have negatives there. These plates in between are doing nothing. They're just basically, you know, the positives cancel the negatives. So all we've done is we've just increased the gap. Yeah? By doing this, we just increase the gap. Add all the gaps together. So it makes sense that the capacitance is going to get less because we increased the gap. So 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 if there's 4 of them. Yeah? Yeah, boom, boom, boom. So there's some justification in the middle, but I don't really care about it. All I want you to know is how do you use your parallel capacitance and how you use your series capacitance. So let's do some. What's the equivalent capacitance of a network that consists of a 3 nanofarad capacitor, a 4 nanofarad capacitor, and a 12 nanofarad capacitor connected in parallel? So you know they're in parallel when there's a junction. There's a splitting or a joining of wires. So these three capacitors are in parallel because of that junction there and that junction there. There's a splitting or a joining of wires. So I'm going to say, well, these are in parallel, and C parallel gets bigger, doesn't it? So that's going to be 4 nanofarads. I'm going to cheat here and just leave it in non-SI units. 4 nanofarads. Do it in order. 3 nanofarads plus 4 nanofarads plus 12 nanofarads. Which equals 3 and 4 makes 7 and 12 makes what? 19? 19 nanofarads. That was simple enough. Which is 19 times 10 to the minus 9 farads. There's my answer. Cool. So that's pretty straightforward. What about when they're in series? They're in series when they're not in parallel. There's no in between, so for any bit of the circuit anyway. So this is 3 nanofarads, 4 nanofarads, and 12 nanofarads. And so I say 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over C series is equal to 1 over 3 plus 1 over 4 plus 1 over 12. And you're probably flashing back to kind of like middle school doing these things, and you're going, well, hold on, common denominator is 12. So that's 4 over 12 plus 3 over 12 plus 1 over 12, which equals 8 over 12. And I can't tell you how many people put down 8 over 12 farads for the answer, which is wrong, because CS is equal to 12 over 8, which equals 1.5 farads. Oh, nanofarads, which equals 1.5 times 10 to the minus 9 farads. And here's the kind of tip. Always check that your parallel combination is bigger than even the biggest individual capacitor. And always check, this is the real check, that your series combination is smaller than even the smallest of the other one. Well, actually, that wouldn't help you in this case because it still looks smaller. But anyway, check. Yeah.
Why do you flip the 8 over 12?
Because it's 1 over CS, not CS. That's what the equation says, 1 over CS. And that's what I'll find. I'll find people will give me a lot of hard work here, and for some reason they don't bother drawing that down, and so they get the answer upside down. And I don't have much sympathy, because I keep telling you to write in sentences. Don't write phrases, write equations. Equations of equal sign of something on one side and the other. So I'm your coach saying, you know, when you're trying to hit a home run, follow through, and my player is stubbornly not following through. So at some point I turn around and say, hey, you know, are you on this team or not? You know, because I'm working really hard to. And so that's what I feel about that is, you know, I get less and less patience as we go on for people not writing incomplete sentences, because I've been saying it for a long time. And they're gonna say it when you get to the next place. So, and it's needless. It's like, doesn't matter how bright you are, writing on complete sentences will improve your performance. So, you know, don't feel bad because you're not Albert Einstein if you're not performing at your fullest extent. And that's not your intelligence, that's your training. What determines, for most people, is not their intelligence, it's their training. It's how much time they can get on task. And being prepared to root out the low skill errors. You know, give points away because of the hard stuff. And forgive yourself that. That's the hard stuff. Do not give stuff away on the easy stuff. Really kind of like take yourself to task about the easy stuff. Because you can do it. You know, you do far more complicated things every day. So don't give away the easy points. So this is a more realistic thing, and I can draw 1,000,000 of these. And, you know, it's one of those things where you've got to prepare in principle. And the hard thing is deciding which bit do you do first. Do you combine the 4 with the 3 and the 12, or the 2 and the 3 and the 12? Or do you do the 3 and the 12? And, you know, how do you do this thing? And it's like eating spaghetti. It's like, where do you begin? You know? And I find the best way is to look for the unambiguous bit. The 4 is in series with the 3 and the 12, but so is the 2. So series bits are not unambiguous, but my word, that parallel bit is unambiguous. Okay, I keep losing the pen. My eyes are a bit cloudy this morning. Sometimes I wear contact lenses, and sometimes my eyes get a bit cloudy, so I have trouble with a little dot. So we do this first, and we go 1 over. So I recognize it's parallel because there's a junction there and a junction there. I go 1 over C parallel equals 1 over C1 plus 1 over C2. No, absolutely nonsense. C parallel equals C1 plus C2. So C parallel is equal to 2 plus 4, which equals 6 farads. So what I do now is I redraw my circuit. That's 12 farads, that's 3 farads, and that's 6 farads. And I go 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over C series equals, sorry, I just got to check on this. 1 over C series equals 1 over 6 plus 1 over 3 plus 1 over 12. So 1 over C series is equal to 2 over 12 plus 4 over 12 plus 1 over 12, which equals 7 over 12. So CS is equal to 12 over 7. And that is my final answer because it's all come down to 1. This is CS. 12 over 7 farads. And I'd like you to go, that's going to be 1.77s are 49, 1.7 farads. Cool. So, bit of a change. I have a parallel plate capacitor, and I have a gap, and I have charges on both sides. And I'd like to know the amount of energy stored. The energy stored inside the electrostatic field. And I actually find the easiest way of getting the energy is by just looking at the graph. As I add more charge, if I could somehow scrape the charge on there, I would notice a bigger potential difference. Or alternatively, as I apply a bigger potential difference, I get more charge. Either way, I have my potential difference and I have my Q, and I have my experimental result. If I double the charge, I double the potential difference. If I triple the potential difference, I triple the charge. It goes hand in hand. The energy is equal to the, well, let's have a look. Let's think about units. What are the units for potential difference? What's it measured in? Volts. Break down volts for me into more fundamental units. What did we say the definition of a volt was? Joules per coulomb, energy per coulomb. So I have joules per coulomb on that axis. And what's the energy, what's the unit for coulomb, for charge? Coulombs. So what's the slope of this going to be? What are the units of the slope? What are the units for the slope? So the slope is joules per coulomb squared. Does that mean anything? Nah, not that I know of. What is the area under the graph? What units is the area the graph going to have? It's going to be joules per coulomb multiplied by coulombs. Let me go through this again. Joules per coulomb multiplied by coulombs equals joules. What do we measure in joules? Energy. Oh, I bet that the energy stored in this capacitor is the area under the graph. If that is the case, then U is going to equal, well, what's that shape? What kind of geometrical shape is it? Oh, a half times delta V times Q. And that's true. So I can actually get my equation, if I forget, I can figure out my equation from just remembering what the graph looks like. But I can do it more mathematically. I say consider charging up a capacitor as the charge increases, the potential difference between the plates increases. Consider an instant in time when the charge on the capacitor is plus Q. The associated potential difference is delta V equals Q over C. That's the definition of capacitance. The work required to transfer delta Q, that little bit of charge, across the capacitor would be my little bit of W is equal to my volts, my energy per coulomb times my number of coulombs, which gives me that. The total work required would be the integral of this. So I integrate this between 0 and the full charge, big Q. And so I get, well, take out your constant is 1 over C, integral of Q dQ. Oh, that's going to be 1/2 Q squared over C. It's a different equation that comes out, but it's the same equation. Let me show you why it's the same equation. I also know down here that charge is equal to delta V times C. So I'm going to play around with this. I'm going to say, well, that equals, let's get rid of the delta V. So this is a half. Instead of delta V, I'm going to put down Q over C times Q, which equals 1/2 Q squared over C. There's another equation. And then on this side, I can say, oh, let's get rid of the Q. So I say this is a half times delta V times delta V times C, which equals 1/2 delta V squared times C. So I have three forms of the equation, and they are saying the same thing. And I could do the same thing here as well. So three forms of the equation. What I do is I know that one really well, and I know that really well, and I can get the rest. But if you do enough homework, you'll get to the stage where you kind of remember all three of them. It's just three basic forms of a similar equation. Okay? Okay. Can you do that one for me, please? Do the top one. How much energy is stored in a 6 farad capacitor that holds 5 coulombs of charge? Oh. Sorry. So let's work some things out then. Sorry about that. You're perfectly right. So let's have a look. Let's have a look. So let's have a look. I'm figuring out myself. So this is my capacitance, and this is my charge. Yes, so let's have a look. Let's have 30 joules. Let's have 15 joules. Let's have 11 joules. Let's have 22 joules. And E, I hope I got the right answer down there. Let's have 75 joules. I'm not even sure I got the right answer in that. Let me think. I'm sorry, I'm just weirding out this morning. So I want to put that on pause so I can think. Yeah, so we had none of the right answers. Okay. So what we do is we say U is equal to 1/2 Q delta V. That's my parent equation. I also know that Q equals delta V times C, so I combine these two. I get 1/2 Q times Q over C, which is 1/2 Q squared over C, and I can work it out. Shame on me, if I'd done more homework last night, those equations would be just like dripping off my tongue. But how much energy is stored in a 9 farad capacitor is fully charged by a 9-volt battery. So let me explain this one as well. So I have a 9-volt battery. It's fully charged. What that means is the 9-volt EMF is now 9 volts potential difference. Even if there's a resistor here, as we'll get to later, what happens is when the current's flowing, then there is a voltage drop across the resistor. But when the current stops flowing, there's no voltage drop across the resistor, and all the voltage drop is across the capacitor. So this is 0 volts potential difference. And that's a little subtlety we'll get to later on in a later chapter. Okay, so now I know my potential difference, and I say I want to find out how much energy. So U equals 1/2 Q delta V. And what do I know? I know my delta V equals 9 volts. What else do I know? I know my C is equal to 9 farads. And I want to know my U. So I got to do some changes here. So I say, oh yeah, but you know, Q is equal to delta V times C. So that's going to give me that 1/2. I want to get rid of my Q. So I'm going to say delta V times C times delta V. So this equals 1/2 delta V squared times C. So this equals 1/2 9 squared times 9, which equals 4.5 times 81. Is that right? Yeah, 4.5 times 81, which is a big number. 729 over 2, which is a big number. 3 what? 364.5. Is that right? I'll take your word for it. And that was the cool. What is the symbol for the oh, joules. Sorry about that. That's you, joules. Cool. Last little bit. Yeah, last little bit. So, if I want to store 10 joules of energy, how big a capacitor do I need? Well, we can figure that out. We can figure out that how much energy is stored per volume. So what we say is energy that is stored in the capacitor is stored as electric field between the plates. And I know from my previous chapter that my potential is equal to minus the electric field times the separation. And I know that for a parallel plate capacitor filled with vacuum or air, so K is 1, C is equal to epsilon naught A over D. So I just combine these together and say, well, U, the energy, is equal to 1/2 C delta V squared, which is 1/2. C is that, so substitute that in. Delta V is that, square it. Turn the... So if you square a negative, what happens? Yeah. So then we get... I see, okay. A good question. I got asked in the last class, and I was like, don't worry about it. But it actually goes away because it's squared. So then we just cancel what we can cancel. And we say, well, okay, we have 1/2 epsilon naught A. D squared over D becomes D E squared. Does this make sense? If I have more area, I should be able to store more charge, which means more energy. What's not so clear is if I have a bigger gap, I can store more energy. Bigger gap for a given field. Yeah, for a given field, a bigger gap means I have to work harder to get it. So that kind of makes sense. The E squared is like one of those things where it's not obvious to me why it's E squared, but it is an E squared. So it kind of makes sense. And then, well, what about per unit volume? So you recognize, oh, look, the area times the gap is the volume inside here. So it's really saying that the energy per volume, that the energy scales with volume. And so I can get my energy per volume is simply 1/2 times epsilon naught times the electric field squared. And that's just an interesting result. In truth, for our upcoming test, I don't expect you to remember these two equations, though I do expect you to be able to work those two equations. So if I say to you, oh, by the way, the energy per density in a capacitor is given by this, plot me a graph of energy versus electric field, you can look at the equation and do it. Or what I worry about is people not knowing what the letters stand for. They blew off the equation and they don't know what the letters stand for. Yes?
You're going to make all these equations too?
No, I got the full equation sheet is there, so you can figure out what's on there. That's a good exercise for you to actually go through the notes and say, that's included, that's included. My other class said it wasn't there, and I apologized profusely. It wasn't because I don't do an equation sheet too, but the full equation's there, so it'll do you good. You'll like it. Comment or question?
Yes. Why is that delta V is negative over there?
Why is delta V?
Why it's in the negative?
No, delta V means your potential difference.
No, I'm talking about the first one.
Yeah, delta V means your potential difference.
It's just in the notes we printed out, there's no negative there.
Oh, there's no negative there?
Not in our notes,
No?
not in the printout.
Bad. And I bet also down there it says UE.
Yes.
Yeah, you see, because I improved these, but I didn't share them with you.
Oh, thanks.
I didn't notice I'd done it. So, yeah, it's just, it should be. We did before when we did potential. Remember the negative sign was there?
Yeah, it was there.
Because if you're a positive charge going with the electric field is like a boulder rolling downhill. So the potential gets delta V is negative when you roll a boulder downhill. So same thing goes for this. Yeah. Cool. I think when I did the notes originally, I knew it squared away, so I didn't care about it. But you know, I'm trying to be a bit more rigorous. Or I just made a silly slip, one or the other.